In this video, we are going to be covering section 4.2, graphs of exponential functions. So the first thing that we have to talk about is going to be properties of transformations of exponential functions. So a transformation of an exponential function has the form f of x equals a times b to the x plus c plus d, where the parent function f of x, which is equal to b to the x for b greater than 0, is shifted horizontally c units to the left, stretch vertically by a factor of absolute value of a if the absolute value of a is greater than 1, compressed vertically by a factor of absolute value of a if the absolute value of a is between 0 and 1, and shifted vertically by d units, and reflected about the x-axis when a is negative, or in other words, less than 0. So the one kind of transformation that we are kind of missing here is, of course, considering a reflection about the y-axis, and that would, of course, happen whenever we have a negative coefficient out in front of the variable x. So if we had something like b to the minus x, then that would be a reflection about the y-axis, of course, which we talked about when we first talked about transformations of functions back in chapter 1. All right, so now that we've talked about the properties, let's get into the examples. So in each of these examples, we are asked to graph each function, state the domain, range, horizontal asymptotes, and y-intercepts. Since we are dealing with exponential functions in all of these examples, the domain for all of the examples is going to be from minus infinity to infinity. So I'm just going to go ahead so that we aren't stating the domain for every single example. And say domain for each function is minus infinity to infinity. All right. So for our first example, we are given the exponential function f of x equals 2 to the x. So for the y-intercept, well, it's just going to be the value of the function at x equals 0. So evaluating f at 0, we get f of 0 equals 2 to the 0. And this is going to be equal to just 1. Okay. And then for the domain, we already know it's going to be from minus infinity to infinity. In other words, all real numbers. For the range, well, this is going to be from 0 to infinity. As x gets very, very small here, we are going to have that the function's values are tending to 0. Of course, we can imagine, 2 to the minus 1 is 1/2, 2 to the minus 2 is 1/4, 2 to the minus 3 is 1/8. So we're getting numbers that are closer and closer to 0 with smaller and smaller input values. And as x gets very, very large, of course, 2 to the x is just going to blow up to infinity. So that's how we get the range of 0 to infinity. And then for horizontal asymptote, so for any exponential function, unless there is some sort of vertical shift or vertical translation going on, every exponential function is otherwise going to have y equals 0, or in other words, the x-axis as its horizontal asymptote. And I'm going to abbreviate horizontal asymptote just by HA. And again, so we said that as x gets very, very small, the values of f are going to be tending to 0. But of course, 2 to the x is never going to equal 0. That is, like, there's no x value that's so small that we are going to end up with 2 to the x somehow equaling 0. It's just going to get very, very close to 0. But it's always going to be positive. All right, and then let's get to graphing. So we can go ahead and plot our y-intercept at 0, 1. And yeah, let me go ahead and write this as a point. So there's our y-intercept. Okay, and then if we wanted to kind of have an accurate sketch of the graph here, we could go ahead and plot some other points. So for instance, when x is equal to 1, well, f of 1 equals 2 to the 1, which is just 2. So it's going to pass through the point 1, 2. And f of 2 is going to equal 2 squared, which is 4. So the graph of f passes through 2, 4. And f of 3 equals 2 to the 3, or in other words, 2 cubed, which equals 8. So it's going to pass through the point 3, 8, which is right up here. And f of minus 1 is going to equal 2 to the minus 1, which is the same as 1/2. So it's going to pass through the point minus 1, 1/2. And yeah, I think we have enough points plotted there. So let's go ahead and connect these guys in a smooth fashion. And as x gets very, very small, we are, of course, just going to be getting ever so closer to that horizontal axis, but never actually crossing or touching it. Again, because we have that horizontal asymptote there. And there is a sketch of the graph of f. Okay, now for example 2. In example 2, we are given the exponential function f of x equals 2 to the minus x. So comparing this second function with the function we had in example 1, well, we should expect this function to just be a reflection about the y-axis for example 2 here. So the graph in example 2, we expect it to just be the graph from example 1 reflected about the y-axis. But let's go ahead and see that, or confirm that rather. So let's start off by just stating what the y-intercept is. So evaluating f at 0, this is equal to 2 to the minus 0, which is just the same as 2 to the 0. So this is still equal to 1. So we still have our y-intercept at 0, 1. Okay, the domain is again all real numbers. The range, well, now this time when x gets very, very small, so large negative numbers in other words, 2 to the minus x is going to blow up. So for instance, 2 to the minus 1, or in other words, f of minus 1 is just equal to 2 to the 1. And then f of minus 2 is going to equal 2 to the minus 2, in other words, 2 squared, so 4. And then f of minus 3 is going to equal 2 to the minus 3, so in other words, 2 cubed. So f of minus 3 is equal to 8. And yeah, as we look at smaller and smaller x values and input them into our function f here in example 2, we are going to get larger and larger values for the output. So the range is still going to have infinity as the right endpoint. And then, well, for the left endpoint, as x gets very, very large here, we will have that f of x is tending to 0. So the range is going to be from 0 to infinity. Okay. And once again, our horizontal asymptote is going to be at y equals 0. Again, there's no sort of vertical shift or translation going on here. So it's going to have the same horizontal asymptote that all exponential functions have as long as they don't have a vertical shift, which is going to be y equals 0. All right, now let's go and sketch its graph. So we have the y-intercept at 0, 1 right there. Yeah, how about I kind of maybe plot the points in a different color? So there's our y-intercept at 0, 1. And this time, so f of minus 1, again, that's going to equal 2 to the minus 1. So in other words, 2 to the 1. So the graph of f in example 2 here is going to pass through the point minus 1, 2 now. So right there. And f of negative 2, again, that was equal to 2 squared. So it's going to pass through the point minus 2, 4, because of course 2 squared is 4. And then f of minus 3 is going to equal 2 cubed, which is 8. So it's going to pass through the point minus 3, 8, which is right there. And also f of 1 is equal to 2 to the minus 1, which again is 1/2. So it's going to pass through the point 1, 1/2. All right, now let's go ahead and connect these points. And that is a sketch of the graph of f of x equals 2 to the minus x. And of course, now that we have its graph sketched, we can compare the graphs from example 1 and example 2, and we can notice that the graph in example 2 is indeed a reflection of the graph from example 1 about the x-axis, or sorry, about the y-axis. And that's kind of up to my drawing skills. Of course, I wouldn't say the graph in example 2 is quite as good as the graph in example 1. Not that I'm saying either of these graphs are that great of sketches. Kind of limited to my drawing abilities, which are not great. All right. On to our next two examples. So in example 3 now, we have f of x equals minus 2 to the x. So, well, this should be a reflection about the x-axis now, because we have a negative leading coefficient, that -1 out in front. So our y-intercept is going to be, well, f of 0 equals minus 2. And of course, the only thing that our variable x is like acting on as the exponent here is 2. It's not the minus. Otherwise, that would be in like parentheses. We would have like minus 2 in parentheses and then x in the exponent. And of course, we've already said that when it comes to our exponential functions, the base b is always going to be greater than 0. So when we look at f of 0, that's equal to minus 2 to the 0, where only 2 is being raised to the 0. So this equals minus 1. And so our y-intercept here in example 3 is going to be at the point 0, -1 now. Okay, and then our domain is still all real numbers. Our range, well, now when x gets very, very large, Well, we know 2 to the x is going to blow up as well too. That is, 2 to the x is going to tend to infinity as x goes to infinity. So since we have that minus out in front, well, when x gets very, very large, the values of f are going to get very, very small. That is, they are going to go to minus infinity. And of course, as x gets very, very small, well, we know that 2 to the x is going to tend to 0. So the range is going to be this time from minus infinity up to 0. And we still are going to have y equals 0 as our horizontal asymptote. Though, of course, this time here, since we are dealing with a reflection about the x-axis, essentially, we are going to approach the horizontal asymptote from below instead of from above. All right, so let's go ahead and graph this guy. So we have our y-intercept here at 0, -1. And then we know that f of 1 is going to equal -2 to the 1. So in other words, -2. So it goes through the point 1, -2. And then we kind of know from our calculations in the first example that its graph is going to pass through the point 2, -4. Again, we have the same values for our function that we had in example 1, except now they've just been changed from positive to negative. And we know that f of 3 is going to be -8. And f of 1 is going to equal -1/2. So like right there. Let's go ahead and connect these guys. And there is the graph for example 3. And of course, if we compare the graph from example 3 with the graph from example 1, well, we're going to see that the graph in example 3 is just a reflection of the graph from example 1 about the x-axis, of course. Okay. And then we have example 4. So in example 4, we are given the exponential function f of x equals 6, and then times 1/3 to the x. So for our y-intercept, well, since a here, the leading coefficient that is equal to a +6, this is essentially going to vertically stretch the values of our exponential function by a factor of 6, or rather the values of the exponential function 1/3 to the x by a factor of 6. And so, for instance, for the y-intercept, this means that it should go from 0,1 to 0,6, but let's double check. F of 0 equals 6 times 1/3 to the 0, which is just going to equal 6 times 1, which is 6. And so our y-intercept is going to be indeed at the point 0,6. Okay. And then the domain is still all real numbers. The range, so when x gets very, very small here, well, 1/3 to the x is actually going to blow up to infinity. So when x is equal to -1, well, we will have 1/3 to the -1, which is the same as 3. So we'll have 6 times 3, which is going to be 18. And then when x is -2, we will have 1/3 to the -2, which is the same as 3 squared. which is 9. And then times 6 is going to give us 54. And so we can see that the values of the function are blowing up to minus infinity, or sorry, to infinity as x goes to minus infinity. And similarly, as x gets very, very large, well, 1 over 3 to the x is going to get very, very small. And multiplying that by 6 isn't going to change much in the long run, which is to say that as x gets very, very large here, the values of f of x tend to 0. So this time our range is going to go back to being 0 to infinity. And yeah, again, so kind of like what we've said about the horizontal asymptotes, when it comes to like the range of our exponential functions, well, if we just consider like the parent function f of x equals b to the x, where b is greater than 0, well, the range is always going to be from 0 to infinity. And the only way that changes is if there is some sort of reflection about the x-axis, so the leading coefficient is negative like we saw in example 3, or there is some sort of vertical shift slash translation, which we'll see in a few examples coming up. So the range is 0 to infinity, and again the horizontal asymptote is going to be y equals 0. Okay. So let's go ahead and sketch our graph for f of x in example 4. So let's plot our y-intercept first. Here at 0, 6. And once again, so f of 1 is equal to 6. I shouldn't say once again. We only talked about negative, evaluating f at negative x values. But anyways, f of 1 is equal to 6 times 1/3 to the 1. So in other words, 6 times 1/3, or 6 over 3, which is going to be the same as 2. So the graph of our function here is going to pass through the point 1, 2, which is right here. And then when x is equal to 2 now, well, we will have f of 2 is equal to 6 times 1/3 squared, or in other words, 6 times 1 over 9, or 6 over 9, which is like 2/3. So it's going to pass through the point 2, 2/3, which is like right there, maybe. Or I guess it should be a little above the halfway point. All right. And then, yeah, so what we did mention was that f of -1 is equal to 18. So we're not going to be able to plot that point on here. So let's just go ahead and sketch, even though we only did 3 points. And there is the sketch of our graph for the function in example 4. Okay, and before we get into the next set of examples, we have like a collection of graphs which are just transformations of the parent function f of x equals e to the x. So here in solid red, we have the graph of f of x equals 2 times e to the x plus 2, and then plus 2. And so this plus 2 here at the very end is, of course, a vertical shift up 2 units. And so, like I've been saying, as we can see from the graph in solid red here, it has a horizontal asymptote with the line y equals 2 now. And then it, of course, has a vertical stretch by a factor of 2 going on here, and it has a horizontal shift to the left by 2 units. Okay, and then the next one, we have graphed here in solid blue, the graph of f of x equals e to the x plus 1. So this is just a shift, a vertical shift, 1 unit upwards. And so again, like I've been saying, we can see that this graph in solid blue now has a horizontal asymptote with y equals 1. And of course, this also causes the range of each of these first two functions that we've considered to change as well too. So for the first function that we talked about, the one whose graph is in solid red here, its range is going to be from 2 to infinity. And for e to the x plus 1, its range is going to be from 1 to infinity. So not does our horizontal asymptote just shift, but also it's going to cause our range to change as well too whenever we have that vertical shift going on. Okay. And then next in the dashed red here, we have the graph of f of x equals minus e to the x minus 1. And so what we have here is going to be, well, just a reflection about the x-axis of the graph in solid blue here. And so, of course, we can see that when we compare the two graphs, the graph in dashed red is indeed a vertical reflection, or in other words, a reflection about the x-axis of the graph in solid blue. And the way we can realize that is, well, minus e to the x minus 1 is equal to minus, and then all in parentheses, e to the x plus 1. So in other words, the function in red is equal to minus 1 times the function in blue. So again, that's just going to be, as we know from chapter 1, a vertical reflection. And of course, since we have this minus 1 here for the vertical shift, again, that's going to cause our horizontal asymptote to move from y equals 0 to y equals negative 1 this time. And as we can see from the graph in dashed red, its range is going to be from minus 1 to minus infinity. So of course, since we start out with a reflection of the parent function e to the x, a vertical reflection, or a reflection about the x-axis to be specific, or to be precise, that causes the range of the parent function 0 to infinity to change to 0 to minus infinity. And then we have that vertical shift downwards by 1 unit, so the range goes from 0 to infinity to minus infinity to 0 to minus infinity to minus 1. Yeah. So I kind of said that wrong earlier when I was talking about the interval for the range. So when we do a vertical reflection of the parent function, the range goes from 0 to infinity to minus infinity, comma 0. And then we shift it down 1 unit to get minus infinity to negative 1. Okay, and then for the graph in dashed blue here, it is the graph of f of x equals 1/2 times e to the x minus 2, and then minus 2. So this time we have a vertical shift down 2 units, and we also have a horizontal shift to the right by 2 units, and a vertical stretch, a vertical compression by a factor of 1/2 of the parent function e to the x. And of course, since we have this vertical shift down 2 units, well, this causes the horizontal asymptote to move to y equals -2 now. So you can see that's going to be the horizontal asymptote right there for our graph in dash blue. Okay, and so let's get into our next examples where we are still wanting to state the where we are still wanting to graph the given exponential function, state the y-intercept, the range, and the horizontal asymptote. Again, for these next two examples, just like any exponential function, the domain is going to be all real numbers or -infinity to infinity. Okay, so for our first example, we have f of x equals 2 to the x plus 6. So for the y-intercept, well, f of 0 is going to equal 2 to the 0 plus 6, which equals 2 to the 6, which, by the way, is equal to 64. Oh. So this is going to be the point 0, 64. Okay, and then the range, well, again, we don't have any sort of vertical reflection or vertical shift going on, so it's just going to be from 0 to infinity. And then for the horizontal asymptote, again, kind of same thing. We don't have any sort of vertical shift going on, so it is still going to be the line y equals 0, or in other words, the x-axis. All right, so we can't really plot our y-intercept here, but what we can plot is so when x is equal to -6, and yeah, I guess I'll actually write out some of our work this time. F of -6 is equal to 2 to the -6 plus 6, which equals 2 to the 0, which equals 1. So our graph is going to go through the point -6, 1, which is going to be right here. And f of -5 is equal to 2 to the -5 plus 6, which equals 2 to the 1, which is going to give us 2. So our graph goes through the point -5, 2. F of -4 is going to equal 2 to the -4 plus 6, which equals 2 squared, which equals 4. So our graph is going to go through the point -4, 4, which is going to be right there. And then f of -3, if you're noticing a pattern here, you can probably already guess this is going to equal 2 cubed. So it's going to equal 2 to the -3 plus 6, which equals 2 cubed, which is going to be 8. So it's going to go through the point -3, 8. And f of -7, how about we do that? It's going to equal 2 to the -1, which is equal to 1/2. So it's going to go through the point -7, 1/2. Okay, and I think we have enough points now. So let's go ahead and connect them. Okay, and there is a sketch of the graph of f of x equals 2 to the x plus 6. What we can notice if we were to compare this with the graph from the very first example, it is just a translation to the left by 6 units of the graph from that very first example. Okay, and then for our next example, we have f of x equals 2 to the x plus 6. So for our y-intercept this time, well, f of 0 is going to equal 2 to the 0 plus 6. So just 1 plus 6, or 7. The domain is still all real numbers. The range, so that's going to change here because we finally have a vertical translation or shift. So this is a vertical shift up by 6 units, and there is no sort of vertical reflection going on. So our range here is just going to be the range of the parent function f of x equals 2 to the x, but shifted up by 6 units. So we're going to go from the interval from 0 to infinity to the interval from 6 to infinity. And this also means our horizontal asymptote has shifted up by 6 units. So now it's going to be y equals 6. And of course, again, the same argument still applies. Like 2 to the x, as x gets very, very small, is going to tend to 0, but it's never going to be negative. And so as x goes to minus infinity, f of x here in example 5, or rather example 6, is going to go to 6, because 2 to the x is going to go to 0, so it's going to go to 6. So we have a horizontal asymptote at y equals 6. So let's go ahead and plot the few points that we can for the graph of f of x in example 6 here. So we have our y-intercept here at 0, 7. And then f of 1 is going to equal 2 to the 1 plus 6. So it's going to equal 2 plus 6, in other words, 8. So our graph goes through the point 1, 8 right there. And then f of 2 is going to equal 2 squared plus 6. So 4 plus 6, or 10. So it's going to go through the point 2, 10 right there. Let me attempt to move this. There. Okay, and then f of minus 1 is going to equal 2 to the minus 1 plus 6. So in other words, 1/2 plus 6, or 6.5. So it's going to be like halfway between 7 and 6. So like right there for that point. Right, and now let's go ahead and connect these guys. Again, we have that horizontal asymptote here at y equals 6, so when we're graphing, we want to make sure to never cross that line. And there is our graph for example 6. All right. In our next example, we are told that the graph of f of x equals 1/2 to the minus x is reflected about the y-axis and compressed vertically by a factor of 1/5. What is the equation of the new function g of x? State its y-intercept, domain, and range. Okay, so since f of x is reflected about the y-axis, this is going to correspond to the transformation of f given by f of minus x. Okay, and then compressed vertically by a factor of 1/5. Well, this is just going to have us multiplying f of x by 1/5. So in other words, we can say that g of x is equal to 1/5 times f of minus x. And then now let's substitute in the rule of assignment for f, or take into consideration that rule of assignment to come up with our equation for g of x. So we'll have 1/5 out in front still, and then f of x equals 1/2 to the minus x, so we'll have 1/2 to the minus, and then minus x, since we have f of negative x. And then we can, of course, simplify the double minuses in the exponent there to rewrite this as 1/5 times 1/2 to the x. Okay, and then the y-intercept for g is going to be, well, g of 0 is equal to 1/5 times 1/2 to the 0, which equals 1/5. So the y-intercept for f of x is, of course, 0, 1. And since g of x is just a vertical compression of f of x by a factor of 1/5, the y-intercept for g of x is, of course, going to be 0, 1/5. Okay, and then the domain is going to be all real numbers still. Again, since g of x is an exponential function, so minus infinity to infinity. And the range well, again, so 1/5 times 1/2 x is always positive for any real value of x. And so the range is going to be some interval that is greater than 0 or has at least 0 as its left endpoint. And of course, we can think, okay, well, again, as 1/2 or as x gets very, very large here, 1/2 to the x is going to get very, very small, or not get very, very small. It's going to get very, very close to 0, because we're going to be looking at, for instance, 1/2 to the 1 is 0.5. 1/2 to the 2 is 1/2 squared, so 1/4, 0.25, so already closer to 0. And then 1/2 to the 3 is going to be 1/2 cubed, so 1/8, so 0.125. And of course, multiplying these values by 1/5 is just going to make them closer to 0. So the left endpoint of our range is again 0. And then, of course, as x gets very, very small, so as x goes to minus infinity, 1/2 to the x is going to blow up. So in other words, g of x goes to infinity as x goes to minus infinity. So the right endpoint of our range is again going to be infinity. And again, we could just reach this conclusion by saying, well, g of x is an exponential function, and there is no sort of vertical reflection or vertical shift going on, so the range is going to be 0 to infinity. In the next example, we are asked to explore and discuss the graphs of f of x equals b to the x and g of x equals 1 over b to the x, and then make a conjecture about the relationship between the graphs of the functions b to the x and 1 over b to the x for any real number b, and to prove that conjecture. So when it comes to looking at some graphs here, we will consider b equals 3. So f of x will be 3 to the x, and g of x, which we'll graph in blue, is going to equal 1/3 to the x. Okay, and now let's go ahead and graph these guys so we can compare. So both these guys have a y-intercept at 0, 1. So 3 to the 0 is going to be 1, which equals 1/3 to the 0. So they're both going to pass through the point 0, 1. Okay, and then when x is equal to 1, well, f of 1 is going to equal 3 to the 1. So 3, so the graph of f will pass through 1, 3. And f of 2 is going to equal 3 squared, so 9. So it's going to pass through the point 2, 9, which is going to be all the way up here. And then f of -1 is going to equal 3 to the -1, which is the same as 1/3. So it's going to pass through the point -1, 1/3, which is like right about here. Okay, and then for the graph of g, the points that we're going to use, well, we already have its y-intercept, and then when x is -1, g of -1 is going to equal 1/3 to the -1, which is the same as 3. So it's going to pass through the point -1, 3. And just to see that real quick, so g of -1 is equal to 1/3 to the -1, which equals, so whenever we have -1 as the exponent, we are just taking the reciprocal of whatever is being raised to the -1, and the reciprocal of 1/3 is just going to be 3 over 1. So this equals 3. Another way we could think about this is that 1/3 is just 3 to the -1 because it's this reciprocal of 3. And so we have 3 to the -1. So the double minuses would just become a positive, so we'd be looking at 3 to the 1. And then g of -2. So this is going to be equal to 1/3 to the -2. And again, we can say that 1/3 is the same as 3 to the -1, and then to the -2. And again, whenever we have power of a power, we take the product of the powers, so we'd have -1 times -2 is going to be a positive 2. So 3 squared, or 9. So the graph of g is going to pass through the point -2, 9. Okay. And then when x is equal to 1, g of 1 is going to equal, well, just 1/3 to the 1. So it's going to pass through the point 1 comma 1/3. So right there. All right, and so now we'll sketch the graph of G in blue and the graph of F in purple. All right, so there's our graph of G, then our graph of F. Okay, and so now that we have both their graphs sketched, we can compare, and what we can notice is that the graph in blue here is just a reflection of the graph in purple about the y-axis. So in other words, a horizontal reflection. Okay, so that's like our conjecture, but then we are asked to prove it. So let's provide some sort of argument to actually show this. So again, when it comes to 1 over b, this is equal to b to the minus 1. So g of x, which is equal to 1 over b to the x, well, we can think about this as being equal to b to the minus 1 and then raised to the x. But then since we have power of a power, we can take the product of the powers and say that this is equal to b to the minus x, which, by the way, is equal to f of minus x, which shows that g of x is just a reflection of f of x about the y-axis. All right, and that's it for section 4.2.